In the last lecture, I introduced you to extraction methods, particularly the liquid-liquid extraction, which we mentioned that it's actually the basis, for chromatography. So the traditional liquid-liquid extraction. And I took you through the theory of liquid-liquid extraction, which is the basis, for column chromatography that we use today. And so in this lecture, I'm gonna very briefly, introduce you to column chromatography. Most of you know a lot about it. And as I have said, it follows the same principles as liquid-liquid chromatography, or even a traditional, thin layer chromatography, which I'm gonna mention in the next slide. And as I said before, the basis of that separation is based on a partitioning effect between two phases, which is often, the aqueous phase and the organic phase, which we discussed in the previous lecture. Okay, organic phase, which we discussed in the previous lecture. So we said, that one phase, is with the column chromatography, one phase is a mobile phase, whereas the other one is a stationary phase, which is typically, pulled inside a column. And so the mobile phase often is the eluent, that pushes the analyte through the column, and the analytes would elute, at different times as they come out. And so whatever is coming out is what often we refer to as the eluate, which is the analytes that have been separated through the column. Now, there are many different types of, chromatography based on the type of column chemistry, that you're using. And so I'd like you guys to at least remember these 5 different types of chromatographies based on the molecular interaction between the analyte and the stationary phase that is locked inside the column. And based on that preferential chemistry, the analyte or the eluates, which we talked about in the previous slide, they come out at different times because they are retained at different times, inside the column. And so whatever you get in the end, after doing column chromatography is what you refer to as a chromatogram, where you've got the detector response as a function of retention time, which relates, of course, to the amount of time the analyte spends inside the column. So there are 5 different types of chromatographies based on that interaction chemistry inside the column. This is what you refer to as adsorption chromatography, is the most traditional. Partition chromatography, ion exchange chromatography, size exclusion, chromatography, and affinity, chromatography, which is often the basis, for proteins separation. So very quickly, adsorption chromatography, traditionally it refers to the stationary phase, and the mobile phase is in a liquid or gas, and the chemistry is based on physical interaction of the analyte onto the stationary phase. And so the kind of interaction is purely based on hydrophobic interactions on the surface, of the stationary phase, which in most cases, is silica gel is what's commonly used. Now, as I've said, this one is a traditional method, adsorption chromatography, that was largely developed, by this gentleman, Michael T. Swart, who developed the thin layer chromatography. And in fact, he's often labeled as a father of chromatography because that's where all chromatography started. and then such, the solute, absorbs on the surface of a solid platform, such as silica gel sheet or even a piece of paper, and the solvent, develops or moves the analyte plainly, on a planar way, on the stationary phase. And so based on the relative interaction between the analyte and, say, the silica gel, in this case, you get a separation in the end. All right, so it's based on physical interaction. Now, the other type of chromatography, that is very common today is what you refer to as the partition chromatography. And that's what you guys did in the lab for gas chromatography, for example. And here you've got the column, but inside the column, you've got liquid stationary phase. So the mobile phase is exactly the same as the adsorption chromatography, but the stationary phase is a liquid. However, the liquid is immobilized inside the column. So essentially it's a liquid, all right, that is immobilized inside the column. And so there are different types of column. You can use a packed column, which are just silica beads, which have been functionalized, with a liquid stationary phase. Or you can use open tubular silica column, which typically, again, is just a few silica tube, and then you make a very thin layer of polymer inside those columns, and you immobilize a liquid, onto that column. So often we refer to them as open tubular columns, which typically look like this: a few silica tube, and then you've got a very thin layer of stationary phase inside those columns. And so the basis of the chemistry in this case is partition equilibria, just like liquid chromatography, where the analyte partitions between the mobile phase and the immobilized liquid phase inside the column. So the partition equilibria. So you just calculate the partition coefficient as we did before, and that's the basis of this type of chemistry. The other type of chromatography is what you refer to as the ion exchange chromatography. And this is where you've got resins, resins that are charged, sometimes negatively charged, sometimes positively charged, and they are packed, inside a column. And so the basis of separation is electrostatic interaction, between the analyte, which should be charged, maybe positively charged, and a resin, which in this case can be negatively charged. And based on that electrostatic interaction, you get your separation done. So you can see in this case, the kind of bonding, that is formed between the analyte and the stationary phase is fairly strong. Sometimes, it's a covalent or electrostatic interaction. So it's a fairly strong bond. And so other than the use of resins or ion exchange chromatography for analytical separation, sometimes we also use it, for example, very commonly, to deionize water. Anytime you guys are using deionized water, essentially what it is you've got a column, and the column has got resins, that electrostatically, attract the ions that could be present in water, and they trap it inside, that resin. And so whatever comes out, essentially doesn't have any ions at all. And so it's used a lot, to deionize water, this type of chromatography. As I've said, the resins can be positively charged if at all you want to remove anions, or they can be negatively charged if at all you want to remove cations. And there are many types of resins, polymer resins out there that you can easily make, like polystyrene. Often you can, this one is polystyrene, for example. And the polystyrene, you can modify it with functional groups such as sulfates. and this one you can see is is a negatively charged, resin that's gonna attract, positively charged ions such as hydronium ions or even cations and so forth. So the other type of chromatography, is called size exclusion chromatography. And in this case, the separation is purely based on, the size of the molecules. So in this case, often you have the column, and then you've got, the beads, that are packed inside the column. And these beads have got holes, okay? And the analytes that are too big, do not get inside the bead, and instead, they just simply random walk through the tube and elute. All right. Whereas on the other hand, analytes that are small, they penetrate the beads, and so based on their size, they are retained very, very strongly. So in size exclusion, which is just a sieve essentially, so these beads are behaving like sieves, the large molecules are excluded, because they do not penetrate inside the beads. The medium-sized, molecules and the small molecules, they penetrate, the beads preferentially. And so in the end, you've got a chromatogram that looks like this. And the early eluting peaks, would be the big molecules. And the latter eluting peaks, would be the small molecules, because they got retained very strongly. Now, there are two types of size exclusion chromatography. There's what they call the gel permeation chromatography and the gel filtration chromatography. And the only difference between the two is the polarity, of the beads or molecular sieves, that are packed inside the column. For GPC, the sieves or the molecular beads are hydrophobic polymers. Okay, they are hydrophobic polymer beads. Whereas with the gel filtration, the beads, are often very hydrophilic, and so they can be used to separate things like proteins. So often you're going to see these one, often they use things like alga, the alga gels, or even things like microcellulose, sometimes it's used a lot with the GPC, or rather with the GFC. Whereas with the GPC, the non-polar types of beads that are used often are plastics such as polystyrene and so on, but at least these beads should have holes in them. And there are many different types of chemistries that you can actually use to make polymers, that has got holes in it. So take note of that difference. The GPC is used to separate, hydrophobic polymers, because the beads are fairly hydrophobic, whereas a GFC, is used to separate, hydrophilic polymers such as proteins, because whatever is packed inside the column is fairly hydrophilic. Things like microcellulose, things like alga, and so forth. So what are the important features in a chromatogram? I think it's important for you guys to remember, as I've said, that the analyte partitions between two phases, say the stationary phase, which is a liquid that is immobilized, and the mobile phase. And so, of course, you know how to calculate the K, which is the relative ratio between the two concentrations. And so based on that, the migration rates inside the columns, are different. And so typically that's how you actually calculate, the retention time, which is the retention time of the analyte minus the amount of time that the solvent, the TM refers to the amount of time that the solvent took to simply percolate, through the column. So if at all I've got any unretained species, meaning there's no chemistry at play, it flashes through the column. So that Tm refers to the amount of time the non-retained species just took, to percolate through the column. Whereas the analytes, retention times, the TR, refers to the retention time, for the retained species. And so the adjusted retention time is a difference between the two. A very important, performance criteria of how good the separation is what you refer to as a capacity factor, or what sometimes they refer to as the retention factor. So take note about how it's calculated. You essentially take the adjusted retention time, divided by, the void time, the amount of time that the unretained species, took, so the TM. Sometimes they call it, the void volume or the void time. Okay, so that's how you calculate the capacity factor. Remember, you can also calculate the capacity factor, based on volume. Because if at all I know the amount of time, that my analyte took to percolate through the column, and the flow rate, is constant, I can calculate, the amount of volume that was dispensed in that amount of time. And so sometimes, people would calculate capacity factor based on the amount of volume of the solvent, that percolated through the column, at TR and at TM, which is the non-retained species. And so you get, the capacity factor. Now, ideally, the capacity factor, should be around 2 to 10, for an optimum separation. If it's too long, it means you're wasting a lot of solvent and a lot of time. If it is too short, it actually means you're not getting good separation. So ideally, a good capacity factor, should be optimally around 2 to around 10. Not too long, not too short. Now, other classifications, of chromatography, other than based of the mechanism, I've just covered the 4 or 5 different types of chromatographies based on the mechanisms. But you can also classify chromatography, based on, based on the mobile phase especially. And so you can have things like liquid chromatography, which refers to the mobile phase being liquid. And of course, the stationary phase is what I just talked about, just a column with liquid that is immobilized, on silica beads often. And also you can have gas chromatography. Again, the mobile phase in this case is a gas. And of course, the column often is a fused silica column or even a packed column as well, that you can use. But you can also have the so-called, which is very new technique actually, very new technique, called supercritical fluid chromatography. And this is where you use a supercritical fluid. A supercritical fluid, is a fluid where, the mobile phase, the characteristic of the mobile phase is such that it's not quite a liquid, nor is it quite a gas. So this is where you often take, a liquid and you pressurize it, and you heat it at the same time, to get what you refer to as a supercritical fluid. Okay, so a good example, is supercritical fluid CO2. You can use it, as a mobile phase, but also you can use, other supercritical fluids as well. But CO2 is a very, very common supercritical fluid, which is a pressurized, gas, and heated at the same time. Okay, it's a fairly new technique, the supercritical fluid extraction. So very quickly, gas chromatography, I'd like you guys to at least be able to remember all the components, of gas chromatography. Of course, the heart of it, is a column. And of course, the type of carrier gas or mobile phase that is typically used. And of course, you need a detector as well. And there are many types of detectors, that you guys should be able to list. You can operate, gas chromatography in a couple of different injection modes. You can inject using the so-called split injection. And of course, you can see The injection pot is just a small oven. So I inject, my sample inside the heated oven, inside the GC. And so with the split injection, this is where a portion of the sample vapor, is vented, whereas only a small portion is injected inside the column. And often the reason you do this is if at all I've got a very concentrated sample. So if at all I've got a very concentrated or a very dirty sample, I don't want to ruin my column, or I don't want to overload my column. So in that case, I would split, my sample inside the injection port, and only a small portion is injected inside the column, whereas the rest, goes to the waste using a vent. Another mode of injection is the splitless injection. And this is where, all the sample vapor is injected or is sucked inside, the GC column, okay? And so often this is where you're doing fairly low, concentrated sample. And especially if at all I want to do good quantitation, ideally, I should be using, the splitless injection, where all the sample goes to the column. Because remember, anytime I'm doing a split, there's an error involved. I cannot reproduce the split, very well. But with a splitless, it's very reproducible. And lastly, the other type of injection, is a so-called on-column injection, where instead of having, these injection pot, I essentially have, my sample being injected, directly, onto the column, and then after that, chromatography takes place. On column injection is especially important if at all the type of sample I'm analyzing is thermally unstable. So for thermally unstable sample, often people would do on-column injection, because if it's heated, in the injection pot, the sample could degrade, and you don't want that. So in that case, you do an on-column injection where the sample is injected right onto the column. So there are many types of GC columns, as I have said. I'd like you guys to at least, be able to enumerate them in case you get such a question in an exam. There's a packed column, not very common anymore unless you're doing things like analysis, of air samples, like pollutants in air. Sometimes, people would use a packed column, all right? So things like nitrogen in air, carbon dioxide in air, people would use a packed column GC. But the most common, types of column these days are the open tubular columns, such as the so-called wall-coated open tubular column, which is where I've got just a polymer, that is coated inside a fused silica tube, all right? In the case of support-coated open tubular column is where I've got, beads, all right, very small beads, essentially nanoparticles, that are coated, inside a capillary tube. And remember, the capillary tube, we say the diameter is very, very small, around 250 microns. So the beads should be much, much smaller, often something like 3 micron, 3 to 30 micron beads. But also there's another type of open tubular column called the porous layer open tubular column. And often this is where you make a polymer around the tube, but the polymer itself is almost like a sieve, meaning it's a porous film. So this one is a very porous film. And I do this a lot in our research group here in McEwan. We develop different types of porous layer open tubular columns using different types of polymerization chemistry. That's all that I'm gonna say about GC chromatography. All right, so the other thing that I'm gonna talk about very, very briefly is the high performance liquid chromatography. And all I'd like you guys to remember is be able to list or even sketch, all right, the different components of LC. That's all I would like you guys, to remember. Different components of LC. And of course, we all know the heart of it, is a column. But in this case, you need a pump so that you can pump, the solvents, through the column. And then lastly, you've got a detector. As you saw in the virtual lab, the type of column that you use, and often most people use C18 columns, is very, very important. And the C18 columns really just refers to silica beads that have been functionalized with a hydrophobic chain of C18 with a hydrocarbon, C18. So there's a C18, a chain, that is functionalized onto the silica capillary, onto the silica bead. And then, of course, you pack them inside the tube. Now, the beads can be 10 micron, they can be 5 micron, or they can be 3 micron. Ideally, you're going to see 3 micron has got better performance, based on what you refer to as a Van Dimter plot, which I won't talk a lot about it. But the Van Dimter plot essentially, tries to profile the height equivalent to a theoretical plate as a function of flow rate. And ideally, the lower the h, the better. All right. And so ideally, you want a very, very small h, height equivalent to a theoretical plate, which essentially refers to the amount of time the analyte percolates between the mobile phase and the stationary phase and back. So that amount of time really is what you call as one height equivalent to a theoretical plate. It refers to that equilibration event, where the analyte goes to the mobile phase and then goes to the stationary phase and back. And of course, we want it to be a very, very short amount of time, okay? And ideally, you want that h, to be fairly small. And that's why I'm saying, for the 3 micron, it gives you a better h. And so often it's a better column to use very, very small beads. So the smaller the beads, often the better the chromatography, okay? The only problem is when you've got very, very small beads, the pressure also increases, you can see, and that is a problem. If the pressure increases, then you get things like leakages and so on, which you do not want. So essentially, in this slide, I'd like you guys to remember the importance, of using very, very small beads because they improve, your separation efficiency because the equilibration event measured in form of height equivalent to a theoretical plate, it's fairly low. But the disadvantage is they result into very high back pressures, meaning that you need very good pumps, you need very good seals that you do not get leakages inside the column. And so lastly, there are many different types of detectors out there that are used with the HPLC. A whole long list here. I won't talk a lot about it, but you're gonna be able to at least list them. And you're gonna see the basis of these detectors is spectroscopy. You can see absorbance spectroscopy, fluorescence spectroscopy, refractive index still is a form of spectroscopy. So you can see light scattering is a form of spectroscopy. So as you can see, most of the detectors, are based on spectroscopy, and the majority of it is absorbance spectroscopy. That's what most often people use. But you also can use, mass spectroscopy as well as, electrochemistry, that we covered, previously. So take note, the limit of detection between all these different types of detectors. So you can see if, for example, you use mass spectrometry, you get very, very low limits of detection, compared to when you're using other forms of spectroscopies, okay? So take a note of the relative limits of detection, that each one of these detectors is able to afford you. And so in my next lecture, really, I'm gonna give you a very brief introduction into some of these spectroscopies, which are the basis, for detectors in liquid chromatography, but also in gas chromatography as well. And I understand, most of us are getting, fairly tired. So I remind you that I've got only one more lecture, short lecture, that again is gonna cover very basic introduction to spectroscopy, and then essentially we are done. So hanging there, we are almost done.